Generation, 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 generators. Okay, so what we're talking about here are electric generators. So, so far we've been talking about like circuits and magnetism. We have this like magical power that comes out, right? We have a voltage, and we're like it's a battery and it's a chemical and whatnot. But how do we actually generate power for your homes? Like we've got electricity everywhere. Right now I'm recording this on a computer which is using electricity. How do we get it? So we do this through an electric generator. And what we're going to talk about here is deriving that generation of electricity and how we actually get this current flowing through the wires and into your homes. Okay, so what we're going to do is we're going to start with a picture. Give me a second to finish drawing this picture. It's always a little bit weird. It always looks a little stupid, so I'm actually going to draw two of them for us. But this is what's happening here. We have a loop of wire, okay? And it's really like a square loop. And I'm doing my best to draw this, but I'm a poor artist. And let's put some points on this. Let's call this, each of these vertexes A, B, C, and D. Let's call the center bar here, which this is like a pivot. There's like a pivot point right here, allowing it to spin. So let's that's a pivot point on the backside too. I can rotate on that. This has some length L, okay? And let's say that from halfway between A and D, this is some value H over 2, and the entire thing is length H. We're also going to, in this case, place this bar, which has the ability to rotate. It's going to be in a magnetic field. So there's going to be a uniform magnetic field running through this bar, or through this loop. Okay, this is our uniform B field, just like that. And what this would look like from the side, if you were drawing it, is it would look like here is a bar, here is some pivot, here are the vertices up here, A and B, and then down here are C and D. And we see a B field, just rocking right through this thing. Okay, so this is kind of like, your 3D view. And then this is what I can draw. I can draw things in 2D. Okay, so that's what we're looking at right now. That's just kind of our picture, what we're having in mind. Now, why this matters is because this bar here is able to pivot and rotate around. Okay, we have, we've got a pivot right here, and this pivot will allow this bar to kind of loop and rotate. Kind of if I have this coaster and it's going like this, okay, it's allowed to pivot and roll. What this is going to cause is, as the B field would be coming through this, when it's at 90, whenever it's parallel here, because remember we talked about the normal vector coming out, when it rolls like this, the B field's going to miss it, which, because the angle's changing, the amount of flux going through this hoop is constantly changing as we spin it. So this changing flux, as we know, is going to induce an EMF. And let's actually figure out what size or the magnitude of that EMF actually is. So when we do this, a few things we have to keep in mind to begin with. Just based off of some right-hand rule principles, wires A and B and wires C and D here, those are actually the only two wires that are going to generate a useful EMF here. And the reason being is that if we actually take a look at wires A, D, and B, C, the direction that they are pointing and how they are moving in the B field, they are actually just going to push their protons and electrons. They're not really pushing the protons, that's kind of weird nucleus stuff, but they're splitting their potentials left and right on the bar. So the bar is very long and they're just splitting left and right here. So you're not actually generating a current through the entire loop system, you're just pushing left and right. So A and D aren't actually going to give us a current that will go around the loop system. They're trying to just build a current like that, or a voltage like that, which that's not going to actually help us here. So we're going to ignore A and D and B and C just due to a right-hand rule and the direction things are going to be moving like that. Okay. If we take a look at just A and B, then let's just look at AB first. Okay. So if we wanted this, we could say that the EMF generated by just A and B is going to equal to, well, that's a moving bar in a B field. So this is going to give us BLV. That's what we've seen in prior videos. And technically, when we think about this, we need this bar to be moving in a perpendicular way to the magnetic field. So that's actually going to have a sine theta. We didn't include that sine of 90 or that sine of theta whenever we derived the BLV equation, but we know it's there. If you go back and watch that video, you can see how that cross product kind of comes there, and we kind of hand wave it away. But technically, there is a sine theta term in there. Now, since we do this for both A, B, and C and D, then what we can say is just the total EMF at the moment should be double that. It should be twice the BLV sine of theta. Okay? So we've got both A and B and C and D. We put them together, we get the whole thing. And the other thing we have to recognize is that while right now we just have one loop of wire, I could have a second loop of wire, placed nearly on top of this, such that the magnetic flux through the first wire is the same magnetic flux through the second loop of wire. And I could do this a third, and a fourth, and a fifth, and a sixth, and a seventh time. And in doing so, because I could have n number of loops, then we can actually say, hey, look, our EMF here is equal to 2 times n number of loops times BLV times the sine of theta. Okay, so we're kind of expanding this. Now, this is where things get a little weird. Because our loop is rotating around the pivot, right? Remember the pivot right here? That's what's causing this tumbling motion. Okay, this is our pivot in 2D. Because our loop is rotating, it's moving in circular motion. We can state that the edge of our kind of coil thing here, or our loop, we can say that this is moving with some velocity in a tangential direction. And if this has a velocity up this way, this velocity will be down here like that, right? Now, if we take a look at this velocity and we look at it with respect to the B field direction, there is some angle, theta here. Well, we know how this angle theta will change in the ideas of circular motion. This angle theta here is going to change by omega multiplied by time. Remember, omega, when we talked about circular motion last year, omega is the idea of a angle, a radian value, or a degrees if you wanted to, but weird, divided by some amount of seconds. And if we multiply omega times a time, well, radians per second times seconds gives us radians, which is just some angle here. So if you wanted to figure out how your angle is changing, well, you need to start thinking about what is your angular velocity. And we actually know some information about our angular velocity. If we know that theta equals omega t, we also know from last year in a very similar line that our velocity is an omega multiplied by r. Remember, we talked about this in class the other day. If you're in a sword fight with a medieval knight, he wants to strike you where the blade is moving the fastest. Well, when he swings the blade, the entire thing is moving with the same omega, the same angular velocity, the same amount of angle is being swept through in the same amount of time. But if you go further away from the pivot, or like the handle of the blade where he's swinging it from, then the tip of the blade is going to have the fastest linear velocity. And that's why the tip of the blade is so dangerous. It's moving faster, and that's why you step in if someone's trying to chop you in half with a sword. Kind of counterintuitive, but it is what it is. So what we can say here is that, look, if we want to figure out what this velocity v is, we know that because this distance here, we said this was h over 2. So we can say that our linear velocity here, v, is going to be omega times h over 2, because that's like our radial position from the center out to our edge. Okay? Now, why would this kind of matter for us? Well, it matters for us because I've got a velocity in here, and I want to get rid of that. I want to start talking about things in terms of rotational quantities, and I've got this theta in here, which is a rotational quantity. So if I take my red equation, and I take the ideas that we just kind of incorporated here, I can say the following. I can say that the EMF generated is 2NBL, and then let's be a little careful here. we know that this velocity here is really going to be omega h over 2. And we know that sine of theta is really sine of omega t. Because those are things I can measure. I can measure the rate I'm spinning this object. So I use omega t equals theta in order to get rid of that theta, and I use omega times h over 2 to get rid of the v. So everything's now in rotational quantities. And from here, I can actually start thinking about some clever things to do algebraically. One of the things I can look at is, I can look at this and say, hey, the 2's, they need to get out of here. I don't like them anymore, right? And furthermore, if this up here in purple was h over 2, that means this entire segment here is h. And if this entire segment here is h, and it's being multiplied by some length here of the bar going across, well, that's actually going to give me all of this, which is an area. So I can actually go back down here and I can say, look, L multiplied with h, these two together are just an area. So let's write it like this now. I can say epsilon equals NB, there's my area, A, here's an omega, and then there's my sine of omega t, which I personally like to write it, if I pull that omega to the front side, I like to think that the EMF generated by a rotating loop in a B field is equal to the WNBA, or the Women's National Basketball Association, sine omega t. And that's it. That will give us the EMF generated as this is spinning at some rate, and even with those sine components there. Interesting thing, the maximum amount we're going to get out of this is just omega NBA, because the maximum value of sine is 1, so that will be the max we're ever going to get on our EMF there. The minimum amount of our EMF is going to be 0, because sine of 0 is 0. So that's the smallest component that sine could ever be. So it's kind of a neat thing there. Furthermore, if just depending on how things are given to you, it's also helpful to remember that omega can be thought of as 2 pi times the frequency. So maybe you're given a frequency here, like it rotates 8 times per second, right? If you multiply that by 2 pi, you'll get an omega out of that you'll be able to use in an equation. So just sometimes they give things in weird ways, they being the College Board or snarky professors in the future. A kind of weird thing about this, though, whenever you're rotating this through, is that because this has this entire sine component here, right, and the WNBA or the omega NBA is going to be a max, what this means is if you go to plot this, whoa, that's a bad looking horizontal line, slightly better. The max is going to be omega NBA, and the min is going to be negative omega NBA. But the rest of it, it just follows a sine function. It goes like this. Poorly drawn by yours truly, but you get the idea. It's just a sine function here, which means that sometimes it's generating a positive EMF and sometimes it's generating a negative EMF. Wouldn't that mean that the current is also switching? That's like saying, if you had a circuit with a resistor, that's like saying current's going this way and then coming back a second later and going, oh wait, no, flip the battery. This is the long. Current's going the other way now. Wait, flip it again. Back and forth, back and forth, back and forth, back and forth. This is kind of weird, isn't it? Well, this is what's known as alternating current, and it is what we use in all of our houses. This is why whenever you go to plug in your phone, you actually have those like phone bricks, because there's something interesting in those bricks that will help you take this current that is positive and negative, and the EMFs that are generated positive and negative, so that the current goes back and forth. It'll turn things into a nice even line of current in a line of EMF that we had previously. Because everything we've done before in this class with circuitry was what's known as direct current, or DC current. This alternating current makes things a little bit weird. It makes some of the math, as you get into higher levels, a little bit more complicated, because you have to start dealing with phasors, which you'll cover later in life. But it really helps us do some things that without alternating current, we wouldn't be able to get the power to your homes as easy as we have it. It'd be much more difficult to generate electricity. Okay, we'll see that idea in a later video on just how transmission lines actually function and what we can do with this idea of an alternating current. Okay, but for right now, this video is finished. You know how to generate an EMF with a generator by this equation right here, and this is the big equation you want. The EMF generated is the WMBA, or the omega MBA sine omega t, with a max, and knowing that you're going to get a really terribly drawn sine function out of that. Okay? So for now, this is finished. Adios, and you all take it easy.